We will now highlight some of the distance protection features that are available in more advanced distance relays, such as the GE Multilin D60. These relays will have both ground and phase distance protection elements available. The ground distance elements will detect faults between a phase and ground, while the phase elements will detect faults between phases. For both of these types of elements, there are 4 zones of protection available. Every zone of protection can be programmed to be protecting in the forward or the reverse direction of the transmission line. These zones can also be programmed to have a mot or quadrilateral shaped protection characteristic. The operating characteristics of each zone can also be set individually. A distance protection relay is used to detect and clear faults that occur on a transmission line. It accomplishes this type of protection for both the phase and ground distance elements by measuring the current and voltage, and using this information, calculates the impedance of the line. If the measured impedance is less than the known impedance of the line, this indicates the line is now shorter than expected, indicating it is faulted. However, due to the inherent inaccuracies of CTs and VTs, the impedance calculations made by the distance relays cannot be guaranteed to be extremely accurate. For example, let's assume the actual impedance of our transmission line is 20 ohms. A fault occurs just past this transmission line on the next adjacent circuit. The actual impedance from the measurement point of the relay to this fault is 20.5 ohms. Due to the inaccuracies in the CTs and VTs along with some transient effects, the relay may measure the impedance to the fault to be less than it actually is, and see the fault as being on the transmission line it is protecting. This would cause the relay to trip the circuit breaker and shut down this transmission line when it did not need to. Because of these inaccuracies, distance zones of protection are not set to stop right at the boundary of a transmission line. Distance relays use multiple zones of protection, with some of them set short to only protect part of a transmission line, and others set longer to protect the entire length of a transmission line, plus some of the next adjacent line. The zones of protection that are set to cover only part of a transmission line are said to be underreaching. The zones of protection that are set to cover more than just that relay's transmission line are said to be overreaching. Zones of protection can also be programmed to protect in either the forward direction or reverse direction. Zones that are set to protect in the forward direction are said to be looking into the line, while zones that are set to protect in the reverse direction are said to be looking out of the line. The strategy used to protect a line is commonly referred to as a scheme. All protection schemes used in distance relaying fit into one of 2 categories: pilot-aided and non-pilot-aided schemes. The main difference between the 2 types of schemes is that the distance relays used in pilot-aided schemes communicate with each other to determine whether the fault is located on the transmission line or not. The relays used in non-pilot-aided schemes do not communicate with each other and instead use delays and other forms of coordination to determine whether the fault is located on the transmission line or not. All coordination in these schemes is done within each individual relay itself. In the category of non-pilot-aided distance protection schemes, there are 2 main types that we will discuss. These are the stepped distance protection scheme and the Zone 1 extension scheme. We will first describe the stepped distance scheme. This scheme is the basic structure for all other distance schemes, so it is important to cover it in great detail. The stepped distance scheme uses 4 different zones of protection to protect its own transmission line, and to act as a backup distance relay to protect transmission lines that are located next to it. We will use the power system shown here to describe how the 4 zones of protection are set and used. The main transmission line we will be protecting will be transmission line number 1, and the relay will be located at the far left of that line. The first zone of protection is set to underreach and extends from the beginning of the transmission line to 80 or 90% of the length of the entire line. This zone is also set to have no time delay. Therefore, if a fault occurs in this zone, the relay can be sure that the fault is located on its transmission line and can trip immediately. Zone number 1 will not protect the last 10 to 20% of the line, which is known as the end zone. Any faults that occur in this area will not be seen by zone number 1 and will have to be cleared by one of the other zones of protection. The second zone of protection is set to overreach and extends from the beginning of the transmission line, past the end of the line, and into the next adjoining transmission line. This is called Zone 2. Zone 2 is usually set to 120% of the impedance of the transmission line. Zone 2 is set in this manner so that it can detect faults that occur in the end zone area that zone number 1 cannot detect. Zone 2 is also always programmed to have a time delay set between 0.25 and 0.4 seconds. Using all of the characteristics we have just discussed, Zone 1 and Zone 2 have the ability of protecting the entire length of the transmission line in the following way. Any faults that occur at the beginning of the transmission line will be picked up by both Zone 1 and Zone 2, as seen by the status of their pickup flags. Since Zone 1 has no intentional time delay, its operate flag will turn on immediately. The Zone 2 operate flag will not yet turn on because it has a time delay programmed within it. The Zone 1 operate flag will then trigger the relay to trip to clear the fault. At that point, the fault will be cleared. The Zone 1 pickup and operate flags will turn off. The Zone 2 pickup flag will turn off, and the Zone 2 operate flag will stay in the off state, with never having turned on. On another occasion, if a fault occurred in the end zone region of the transmission line, the two zones would act differently. The fault does not lie within the zone of protection of zone number 1. Therefore, Zone 1 will not pick up. The fault does lie within the zone of protection of zone number 2. Therefore, Zone 2 will pick up. After the Zone 2 time delay has expired, the Zone 2 operate flag will change to the on state and trigger the relay to trip and clear the fault. Once the fault is cleared, both the pickup and operate flags of Zone 2 will turn off. You may be wondering what would happen if a fault occurred on the adjacent transmission line but still within the Zone 2 area of protection. Normally, after the Zone 2 time delay expired, the relay would trip the unfaulted transmission line. However, you have to remember that every adjacent transmission line is protected by its own distance relay. This fault would fall into the second relay's first zone of protection, and the fault would be cleared before the timer of Zone 2 in the first relay expired. The third zone of protection is set to overreach past the end of the second adjacent transmission line. The third zone is used to act as a backup for that next adjacent transmission line in case the protection on that transmission line fails. For this reason, Zone 3 is usually set to extend to the same point as Zone number 2 of the adjacent transmission line, so a setting of 220% of the impedance of its own transmission line is often selected if Line 1 and Line 2's impedances are the same. Zone 3 must have a time delay that is longer than the operate time of Zone number 2 of the adjacent transmission line. A time delay of 1 second is commonly used. Zone 4 is used as backup protection for a small portion of the adjacent transmission line in the reverse direction. The operation of this zone is usually time delayed to allow the first zone and second zone of that adjacent transmission line to operate first. A time delay of 750 milliseconds to 1 second is common. Once each of the 4 zones have been set, the stepped distance scheme to control the breaker on the left side of the transmission line is complete. However, the breaker on both ends of the transmission line must be opened to completely clear a fault. Therefore, another distance relay must be located on the right end of the transmission line to control that breaker. The relay on the right needs to be programmed with the same characteristics as the relay on the left. However, this one will be set up to be protecting in the opposite direction. Now, the zones of protection of each relay will detect any faults that occur on our protected transmission line. These relays will then proceed to open the breaker and clear the fault from their own respective end of the line. Each relay will also have ground stepped distance zones of protection, which are identical to that of the phase stepped distance zones. The difference being that the ground distance elements are used to detect single phase to ground faults. The other type of non-pilot aided scheme we will discuss is the Zone 1 extension scheme. The Zone 1 extension scheme is an enhancement to the stepped distance scheme covered in the previous section. This protection scheme operates on the principle that most transmission line faults are transient in nature, which means the fault is not permanent. For example, the most common cause of faults on transmission lines is lightning. If lightning strikes a transmission line, it ionizes the air, which reduces the resistance between the different phases of the line. This reduced resistance allows for a path for current to flow, and hence creates a fault. Once the transmission line is tripped and the fault is cleared, the ionized air is removed and there no longer exists a path for current to flow. Closing the transmission line circuit breaker at this point would re-energize the line and transmission of power could resume. As mentioned before, the Zone 1 extension scheme is like the stepped distance scheme where it has 4 zones of protection. The difference between the two schemes is that in the Zone 1 extension scheme, an additional Zone 1 impedance setting is set higher to overreach into the next adjacent transmission line. The impedance of this extended Zone 1, which is labeled Z1X, is usually set to the same impedance as the Zone 2 setting of 120% of the impedance of the entire transmission line. This extended Zone 1 is used by the distance relay until it detects a fault within this zone of protection. Once a fault is detected, the relay will immediately trip the transmission line since there is no delay in the operation in the extended Zone 1 element. As you can see, the relay will trip the line even though the fault may exist in the area located in the extended Zone 1 but be in the adjacent transmission line. Once the breaker is opened and the fault is cleared, the relay will then automatically reclose the breaker and re-energize the transmission line. Once the line has been reclosed, the relay will then use the standard Zone 1 characteristic and now underreach to only protect an area within its own transmission line. If the fault that occurred was a permanent fault and the fault is located within the transmission line's newly shortened Zone 1, the relay will trip and again open the circuit breaker to clear the fault. If the fault was transient in nature, the first occurrence of tripping the line would have removed the fault and transmission of power would resume. If the fault that occurred was a permanent fault and reappeared after the reclosing, but was not located in the new shortened Zone 1 protected area, the relay would not pick this up for a second time in Zone 1 and not trip to try to clear the fault. The permanent fault would then be cleared by the Zone 2 protection after the set time delay if the fault fell inside the transmission line's end zone area. If the permanent fault was picked up by the relay Zone 2 because it was located at the beginning of the next adjoining transmission line, the relay protecting that transmission line would pick it up in its Zone 1 of protection and clear the fault. The disadvantage of the Zone 1 extension scheme is that external faults within the extended Zone 1 reach of the relay trip the breaker instantaneously, even if that breaker did not need to be tripped. This needless tripping increases the amount of breaker maintenance needed and causes a needless loss of power supply to some customers. All transmission line distance protection schemes that fit into the category of pilot-aided schemes are based on the basic concept of stepped distance protection schemes. On a stepped distance scheme, any fault that occurs in the midpoint of a transmission line that fits into both of the relay's Zone 1 will be cleared instantly by the relay located at each end of the line. However, if the fault is located on one of the end zones of the transmission line, which is also known as a close-in fault, it will not be cleared instantly at both ends of the transmission line. The fault will be cleared instantly by Zone 1 of the relay that is located near the fault, but will not be cleared instantly by the relay at the far end of the line because the fault did not fall in its Zone 1. The fault will not be cleared at the far end of the transmission line until the time delay in Zone 2 of that relay has expired. You'll remember that the time delay for Zone 2 operation is usually in the range of 250 to 400 milliseconds. The main reason to modify and improve upon the stepped distance scheme using pilot-aided schemes is to speed up the performance of clearing faults that occur in this end zone of the transmission line. Pilot schemes speed up the clearing of faults that occur on the transmission line and inside Zone 2 of the local relay by communicating with the relay at the remote end of the line to determine if the fault is actually on the transmission line. Therefore, all pilot-aided schemes require a communication channel be provided between the two relays. Over this communication channel, the two relays share information regarding the general location of the fault, allowing the clearing of faults on the transmission line to occur as fast as possible. The most common pilot-aided schemes are the DTT scheme, which stands for Direct Underreaching Transfer Trip, the PUTT scheme, which stands for Permissive Underreaching Transfer Trip, the POTT scheme, which stands for Permissive Overreaching Transfer Trip, the Hybrid POTT scheme, which stands for the Hybrid Permissive Overreaching Transfer Trip, and the Directional Blocking scheme. We'll discuss all of these schemes in the following sections. A fault that occurs in the end zone of a transmission line normally will not be fully cleared until the time delay of the Zone 2 protection element has expired. The DTT scheme, which stands for the Direct Underreaching Transfer Trip scheme, is used to reduce the amount of time needed to wait before clearing a fault that occurs in this end zone of a transmission line. As for all pilot schemes, there must be a communication channel set up between the distance relays at each end of the line. This communication channel can be one of many different configurations. The communication channel may have the ability to only send one bit of data back and forth between the relays, such as a power line carrier communication link, or may be able to send multiple pieces of data back and forth between the two relays, such as a fiber optic or microwave link. First, each of the relays must also have all of its 4 zones of protection set up to operate as a standard stepped distance application. For the examples we will be using in this section, we will label the two distance relays that are protecting the transmission line in the following way. The distance relay that is located on the left side of the transmission line will be called the local relay. The distance relay that is located on the right side of the transmission line will be called the remote relay. When a fault occurs in the middle of the transmission line using the DTT scheme, or both zone 1s of the local and the remote relays, the relays will trip and clear the fault instantly at both ends of the line. This is similar to the stepped distance scheme. Faults that occur in the local relay's end zone of the transmission line will be cleared at the remote end of the line instantly by the zone 1 element of the remote relay. The breaker at the local end of the line would normally not trip until the timer of zone 2 had expired. Using the DTT scheme, if a fault occurred in the transmission line end zone, the remote relay that identified the fault in its zone 1 will immediately trip the breaker on its side of the line. Upon detecting this fault in its zone 1, the remote D60 will also immediately send a signal, which is known as a key, over the communication channel to the local relay located at the other end of the line. This is where the term underreaching came from, because the keying signal is initiated by identifying a fault within the relay's underreaching zone 1. As soon as the local relay receives the DTT key from the remote relay, it will immediately trip its breaker, thus clearing the fault on the transmission line. The important thing to note with this scheme is that the local relay will trip as soon as it gets a transfer trip signal from the remote relay without requiring any indication of a fault within its own zones of protection, hence the term direct transfer trip. The PUTT pilot-aided scheme stands for the Permissive Underreaching Transfer Trip Scheme. Just like the DTT scheme, the PUTT scheme is used to speed up the clearing of faults that occur in the end zone of a transmission line. For this scheme, as for all pilot-aided schemes, a communication channel must be provided between the two relays located at each end of the transmission line. In the PUTT scheme, the remote distance relay sends a PUTT key signal to the local relay whenever it detects that a fault exists within its underreaching Zone 1 area of protection. This is where the expression underreaching comes from in the term permissive underreaching transfer trip. The difference between the DTT scheme and the PUTT scheme is what the local relay does when it receives the key signal from the remote relay. In the DTT scheme, the local relay trips as soon as it received the key signal. In the PUTT scheme, the local distance relay PUTT logic will now only trip the breaker if it receives the PUTT key and the local relay has detected a fault within its Zone 2 area of protection. If the local distance relay received the PUTT key and it does not detect a fault within its Zone 2 area of protection, the PUTT scheme will not cause the local distance relay to trip. Therefore, the distance relay's PUTT scheme uses the key from the remote relay as a permissive signal that allows it to trip if the local relay detects a possible fault on the transmission line. Hence the term permissive underreaching transfer trip. When a fault occurs on a transmission line somewhere on the line, currents are flowing to ground. Measuring the direction of the flow of the ground current is used to assist some of the pilot-aided distance protection schemes in determining if the fault and the source of the ground current are located on their transmission lines. The ground directional overcurrent elements let the pilot-aided schemes know if the ground current rises above a minimum set level, and if it does, what direction the ground current is flowing. The ground directional overcurrent elements are used by the pilot-aided schemes because they are sometimes more sensitive to detecting faults than the distance elements are when the source has a weak infeed or high system impedance ratio. The benefits of using ground directional functions in pilot schemes are that the zero sequence and negative sequence currents that are used to detect the direction of ground currents do not contain very many load components. Therefore, the pickup levels for the ground directional elements can be set very low and thus are very sensitive. The ground directional elements are also very fast operating because the zero sequence and negative sequence currents build up from practically a zero pre-fault value. Also, since there was no ground current before the fault, the pre-fault zero sequence and negative sequence currents do not bias the direction of the developing fault components. The POTT pilot-aided scheme stands for the Permissive Overreaching Transfer Trip Scheme. Like the other pilot-aided schemes, it is used to speed up the clearing of faults that occur in the end zone of a transmission line. Again, a communication channel must be provided between the two relays for the POTT scheme to operate. In the POTT scheme, the remote distance relay speeds up the tripping of an end zone fault by sending a permission to trip key from the remote relay to the local relay under two conditions. The first condition is when the remote relay detects a fault occurring within its overreaching zone 2. This is where the expression overreaching comes from in the term permissive overreaching transfer trip. The second condition under which the remote relay will send a permissive key is when it detects that ground current is flowing in its forward direction. Therefore, the remote relay's forward negative sequence directional overcurrent element, or its forward neutral directional overcurrent element's operation, will also cause the remote relay to send a POTT key to the local relay, in addition to the overreaching Zone 2 pickup flag. In the POTT scheme, the local relay POTT logic will only cause the breaker to trip if it gets the POTT key and the local relay has detected a fault within its Zone 2 area of protection, or it detects that ground current is flowing in its forward direction if this function is enabled. As a result, either the local relay's forward negative sequence directional overcurrent element or the forward neutral directional overcurrent element, as well as the picking up of a Zone 2 fault, will cause the POTT scheme to trip the breaker once it has received a permissive key from the remote relay. Any combination of the two reasons the remote D60 sends transmit keys and the two reasons the local relay identifies a fault will isolate the transmission line and verify the fault is located on the transmission line we are protecting. As shown in Diagram 1, if Zone 2 of both relays identifies a fault, it is a clear indication that the fault is on the transmission line, so both relays will trip their respective breakers. In Diagram 2, the remote Zone 2 indicates that the fault is located to the left of the remote relay, and the forward flow of ground current, as seen by the local relay, indicates that the fault is to the right of it. Therefore, the fault is on the transmission line, and both relays will trip their breakers. In Diagram 3, the forward flowing ground current of the remote relay and the Zone 2 picking up on the local relay is a clear indication that the fault is on the transmission line, and so both breakers will be tripped. Finally, in Diagram 4, the direction of ground current detected by both relays is flowing into the transmission line, which is again a clear indication that the transmission line is faulted, resulting in the tripping of both breakers. The hybrid POTT, or hybrid permissive overreaching transfer trip scheme, is a modification of the POTT scheme, which adds an extra degree of security and additional protection for transmission lines that have a weak in-feed source. The hybrid POTT scheme works in the very same way as the POTT scheme to speed up the clearing of end zone faults. In this scheme, both a Zone 2 fault and forward-flowing ground current being detected by the remote distance relay will send a permissive key to the local distance relay, thus allowing it to trip. The local distance relay also tries to detect reverse ground current or a Zone 4 fault. If either reverse ground current or a fault is picked up in Zone 4, the hybrid POTT scheme is blocked from tripping, resulting in additional security. The other advantage of the hybrid POTT scheme over the POTT scheme is its ability to trip on faults that are fed by a source that has a high source impedance. This is also referred to as a weak in-feed. When a fault occurs on the transmission line with a weak in-feed that is located close to the local distance relay, the characteristics of the transmission line will operate in the following way. The voltage measured by the local distance relay will be very close to zero. The current flowing through the local distance relay CTs will not be very high. Therefore, the distance zones of protection may not pick up because the fault current is below the current supervision level, as was discussed in the zones of protection section. Also, the zero sequence and negative sequence current will be almost zero. Therefore, the forward and reverse ground directional overcurrent elements will not operate. Even though none of the distance relay's protection elements have picked up the faulted line still needs to be cleared. The weak in-feed feature of advanced distance relays can detect this condition and correctly trip the relay. The directional blocking scheme is one of the most popular types of teleprotection schemes used in distance applications today. Again, we should state that the purpose of the scheme is to speed up the tripping of faults that occur in the end zone of a transmission line. As with all pilot-aided schemes, a communication channel must be provided between the two relays located at each end of the transmission line for the directional blocking scheme to operate. In the directional blocking scheme, the local distance relay has an additional delay timer that is started by the detecting of either a fault inside its Zone 2 area of protection or the detection of ground current flowing in the forward direction. This timer is set considerably shorter than the normal Zone 2 delay. When this additional timer expires, the local distance relay will trip the local breaker unless it receives a block message or key from the remote distance relay. The remote relay will only send this blocking key if it detects that the fault is located in its Zone 4 area of protection, or it detects that ground current is flowing in the reverse direction, both of which would indicate an external fault. The last subject we will deal with in distance relaying is power swing blocking. A stable power swing can be seen as a condition where our system loses synchronism for a short period of time with our neighboring system and then later regains synchronism. Two reasons that a power swing such as this can occur are: one of the systems loses a significant amount of generation, therefore instantly becomes much weaker, and the load of the system remains constant, or the system is already weak and the load suddenly increases substantially. During a power swing, the voltages and currents will fluctuate significantly, drastically affecting the value of the measured impedance of the line. The plotted impedance as measured by the distance relay will slowly swing from our load point into the distance operating zones and then back out to a load point if system regains synchronism. The power swing blocking feature on advanced distance relays can detect that the impedance swing is a recoverable power swing and will block the distance zones from operating. This is detected by creating an additional impedance zone located around the operating impedance zones as shown. A stable power swing is detected if the impedance of the system moves into this new impedance zone for an extended period of time. Under this condition, the distance protection will be blocked. If this swing were a real fault that entered the power swing blocking area, it would move very fast through this additional area and into the operating impedance zone. The power swing blocking characteristics must be configured to be much larger than the distance Zone 1 characteristic to ensure a stable power swing is detected long before Zone 1's operating characteristic is reached. The outer boundaries of the two larger zones in this diagram form a tomato-shaped zone, while the area of overlap of these two zones form an inner lens-shaped zone. The resulting tomato-shaped outer zone is what is used to detect the presence of a power swing and sets the block of the distance element. If the impedance enters the lens shape, the relay no longer sees this as a power swing, but maintains the block signal for a short time to allow the system impedance to leave this area, as will happen in a stable swing. With the advent of high-speed, low-cost LAN technology, a new form of line protection known as line current differential relaying is becoming more popular due to its speed, sensitivity, immunity to power swings, and being a form of unit protection. Unit protection means the zone of protection covers the complete power system component without overreaching. Line current differential relaying measures and compares the current at both ends of the line using two separate relays and a communications link. The zone of protection is the segment of the line between the two sets of CTs. Theoretically, the sum of the two currents should be zero. If there is a difference beyond a reasonable amount, there is a fault on the line, and so both relays trip their respective breakers, isolating the line. The communication link requirements for differential relaying can be quite modest by today's standards. For example, the GE Multilin L90 current differential relay requires only a 64 kilobytes per second communication link. To enhance reliability, modern utility class line current differential relays will provide built-in distance backup in the event of a communication link failure. For the following examples, we will be using the GE Multilin L90 relays. Let's first take a look at a two-terminal application to better understand the operation of line current differential relaying. Upon power-up, the two relays first synchronize their internal clocks via the communication link. Each relay then measures the current at its CTs and sends this information along with a timestamp to the other relay. Using a form of the percent differential element, each relay compares the current measured at its location with a value of current having the same timestamp that was received from the remote location. If there is more than an acceptable error, there is a fault on the line, and the element in both relays will operate to isolate that section of line from the rest of the power system. The L90 relays support both 2 and 3 terminal configurations. The relays in a 3-terminal configuration will behave in the same fashion as the 2-terminal configuration, with each relay making its own decision as to whether it will trip. In this way, all L90 relays are said to act as masters. If there is a failure of one communication channel path, the relays will automatically switch to a backup master-slave mode. The relay that is still in communication to the other two relays will be the master, and the other two will switch to slave mode. The master relay will perform the differential element calculations for its location and both of the slave locations. If a fault occurs, the master will either trip its own breaker and/or send the appropriate signal to one or both of the slave relays to clear the fault. With line current differential relaying, there are two common types of transfer trips that can be sent: the 87L direct transfer trip and the key direct transfer trip. The 87L direct transfer trip is sent from the master's line differential element and causes the slave that receives the transfer trip to trip. The key direct transfer trip is sent by another function such as breaker failure. The basic premise for the operation of differential protection schemes is that the sum of the currents entering the protected zone is zero. In the case of a power system transmission line, this is not entirely true because of the capacitive charging current of the line. For short transmission lines, the charging current is a small factor and can be treated as an unknown error. In this circumstance, the relays can be applied without voltage sensors. The line charging current will be included as a constant term in the total variance, increasing the differential restraint current. For long transmission lines, the charging current is a significant factor and should be calculated by the relay to provide increased sensitivity to fault current. Compensation for charging current requires that the voltage at the terminals is supplied to the relays. The algorithm calculates the capacitance times the change in voltage over the change in time for each phase, which is then subtracted from the measured currents at both ends of the line. This is a simple approach that provides adequate compensation of the capacitive current at the fundamental power system frequency. Traveling waves on the transmission line are not compensated for and contribute to restraint by increasing allowable error in the setting of the differential error. If the VTs are connected in Y, the compensation is accurate for both balanced conditions. For example, all positive, negative, and zero sequence components of the charging current are compensated. If the VTs are connected in delta, the compensation is accurate for positive and negative sequence components of the charging current. Since the zero sequence voltage is not available, the relay cannot compensate for the zero sequence current. Let's look at an example of a breaker failure protective element. In this example, the protective relays operate correctly, but the associated circuit breaker fails to clear the fault because of some malfunction within the breaker or its control circuits. The fault will now remain on the system until some other means is used to clear it. In our example, the primary or backup relays start a timer once a fault has been detected. The timer will then time out and send a trip signal to all breakers that can feed the failed breaker with power.